All right, thank you. Okay. Hopefully this works. Okay, so this title does not match the title that was promised, because originally I was going to do some kind of a survey, non-smooth optimization, stochastic gradients, and so on and so forth. But then I sort of realized that it would be too much for 40 minutes and this late in the day. So instead, I'm going to talk about one topic, and there will be lots of pictures. It will be fluffy, and hopefully the ideas will be clear. Okay, so this is joint work with Damick Davis from Cornell. Oh, I should mention, okay, so there will be no random matrix theory in this talk, and there will be no numerical linear algebra. Just so we're clear, there will be eigenvalues that appear at some point. There'll be one eigenvalue that appears at some point. But there will be randomness. Okay. Okay, so here's the whole entire talk is going to be just one question and one question only. Suppose I have a typical function, whatever that means, and I apply a typical algorithm, whatever that means, like gradient descent or something akin to gradient descent, or if your function is not smooth, you have to sort of modify gradient descent in some way. Does such an algorithm actually converge to local minimizers? Okay, we would hope so, because such algorithms are used all the time. And really, if your problem is non-convex, the best you can hope for is convergence to local minimizers. However, that's not the typical guarantee of algorithms. The typical guarantee of algorithms is that the gradient, or something akin to the gradient for non-smooth problems, tends to 0. So you converge only to critical points. And it's now widely understood that lots of problems have critical points that are very pathological, but local minimizers are good. And so really you want to make sure that your algorithms converge to true extrema, true local minimizers, instead of just points where the gradient is 0. Okay, so roughly speaking, what you want to ensure is this kind of picture. So here's a critical point with negative curvature. So it's not locally minimizing. So you want to make sure, you want to argue that if you have some kind of an algorithm, that it's not going to be attracted to such a point, and instead maybe we'll pass by a critical point that's not locally minimizing and go away from it eventually, and end up only at extrema, only local minimizers. Okay, so that's the name of the game. Okay, so like I said, the questions and the answers are going to be a little fluffy. So there is a kind of answer to this question if your function is smooth. So now I need to be a little bit more precise what I mean by typical. Okay, so here's a basic fact. So if I take a function that's smooth, I can make it be typical by adding a little perturbation. So suppose I take my function, smooth, sufficiently smooth, I add a little linear perturbation. Then if I take a generic vector v, so Lebesgue, full Lebesgue measure, and I take a random x0, again, full Lebesgue measure, and I initialize gradient descent x0 on the function f sub v, then indeed it will converge to a local minimizer of f sub v, not just a critical point, but truly to a local minimizer. Okay, and in fact, I will explain why this is the case on the next slide. Okay, so this is sort of the results I'm going to be interested in are of this flavor. Generic means tilt, and maybe random initialization. Okay, and so now the question I want to, and this is somewhat classical. Okay, so I'll explain in a second. Okay, so the question that I want to understand is, can something like this be true for non-smooth optimization? Okay, so we optimize non-smooth functions all the time, whether you do deep neural networks or anything, robust control, all sorts of things. Non-smoothness arises very naturally. Well, there'll be some examples in a little bit. And so can something like this be true for non-smooth optimization? And there is a difficulty. There's like a conceptual fundamental difficulty in answering this question. And it's the following. Okay, what do we know about smooth functions? We kind of know what smooth functions that are non-degenerate look like because of Moore's lemma. Moore's lemma tells us if I have a critical point and the Hessian is non-degenerate, non-singular, then up to a diffeomorphism, this function is quadratic. So if we understand what happens on simple quadratics, we sort of understand in a fluffy way what happens for smooth functions. For non-smooth functions, there is no Moore's lemma. There is no canonical representation of what a non-smooth function looks like around the critical point. And this is a fundamental difficulty in answering questions of this type. But I will show you there's something that replaces the Morse lemma, and that's good enough for these purposes. Okay, so that's what this talk is about. Answering this question positively with a little bit of subtlety, and so on and so forth. Okay, so that's what I'll talk about. Okay, so here's the outline. So I will actually I'll actually explain the proof of this theorem. Why is this the case for smooth optimization? Why does gradient descent, for example, on a typical function randomly initialized, why does it only converge to local minimizers? And then I'll explain why this sort of argument all breaks down for non-smooth problems, and we'll see that there needs to be a key definition, a basic new definition that captures this notion of some kind of canonical representation, something that's like Morse. Okay, and that definition will be an active strict saddle property. And then I will sort of explain this is somehow a very generic property, and then I'll finally answer the question going back to algorithms and show that various algorithms indeed only converge to local minimizers. So that's the game plan. Feel free to interrupt me at any time, by the way, and ask questions. Okay, so let's go through this. So let me explain why is this the case? Kind of this sort of result. Okay, for smooth optimization. Okay, so suppose I give you a generic smooth function. So the word generic literally means what was on the previous slide. You take any f and you add to it the linear tilt, and you say, okay, for almost every linear perturbation v, the following is true. So that's what generic means. That's what. Okay, so if I give you generic C2 smooth function f, then every critical point is either a local, this is a basic fact, it's either a local minimizer or a strict saddle, okay? Which means that the minimal eigenvalue of the Hessian is negative. This is a consequence of Sartre's theorem. It says that if I have a sufficiently smooth function, then at every critical point, the Hessian is going to be non-degenerate, which means that either all the eigenvalues are strictly positive, so it's a local minimizer, or one of them is negative, so it's a strict saddle. So that's a basic fact. So since we're only interested in generic functions, we might as well therefore focus on what happens around strict saddles. So that's the name of the game. You want to ask yourself, why is it the case that if I look at a critical point, which with negative curvature, why is it the case that these points are bypassed by typical algorithms? Well, that's the name of the game. Okay, so the way you do this is you set up, you kind of go back to fixed point ideas. So your algorithm is really, whatever algorithms you're interested in, you model it as a fixed point equation, fixed point iteration. So for example, gradient descent corresponds to a fixed point where you iterate identity minus some step size parameter grad f, right? So you iterate this, and this is gradient descent. Okay, so you have a fixed point thing, fixed point equation. Now it turns out, so just abstract away your algorithm that you want to understand as a fixed point, as a map, an operator, T. Now, what you typically say is, okay, strict saddles, it's this property of your function, are related to fixed points of T, hopefully in such a way that unstable fixed points, that those strict saddles correspond to unstable fixed points of T, which means that the Jacobian of T has an eigenvalue of magnitude bigger than 1. So in particular, again, let's look at the gradient descent system. So if you have negative, if the Hessian of f has negative eigenvalue, that means that this operator has an eigenvalue that's strictly positive, so it's unstable. All right, good. And now you just appeal to a hammer. Boom. Okay, once you verify this, you identify strict saddle points are actually unstable fixed points of T. Now you hit this thing with a hammer from dynamic systems, which is the center stable manifold theorem. Center stable manifold theorem says the following. Suppose I have a fixed point iteration. Let's look at all the points that are attracted to an unstable point. Then that set of points that are attracted to it eventually converge by the fixed point iteration has a manifold structure. And it has codimension at least 1. So in particular, the set of initializations has Lebesgue measure 0. So as roughly speaking, therefore, if you initialize at random, you never hit this set of points that are attracted to the unstable fixed points. And that's the recipe. Okay, so that's how you do the thing, for example, for gradient descent. But you can do this procedure, and it has been done by these authors. for other algorithms like coordinate descent and all sorts of stuff. This is the same procedure. Okay, so good. So this is fundamentally relies on smoothness. Okay, you need to talk about the Jacobian of t, so you need t to be differentiable, etc., and so on and so forth. So the question is, can all of this be relaxed if you drop smoothness of the fixed point iteration? And the answer is no, not directly. Yeah.
So I mean, the stable manifold theorem gives you kind of
locally
kind of extending it, but like
yeah, I lied. Yeah, I lied. Yeah, okay. So it's local, but then if your update map, its inverse is Lipschitz, you can pull back 0 measure sets to 0 measure sets to 0 measure sets, and then cover everything with 0 measure. So that works. So you need the inverse of your t. You need t to be invertible and the inverse to be Lipschitz globally, and then you can pull back from neighborhoods because you only do finitely many iterations. So it's yeah.
So okay, so definitely enough to make sure you don't stay up.
Yes, there's papers that quantify this. So actually, like for example, gradient descent can be arbitrarily slow, but if you introduce certain perturbations to it based on a certain noise injection, you can get rates of convergence. There's some famous papers of Lee, Kakade, and Mike Jordan and others. I forget where you can get some rates and stuff. So those things, so these things are actually become okay. So the statement so the only randomness, the only time tilt will appear is here. It's to ensure that every critical point has negative curvature. Everything else just depends on the minimal eigenvalue of the Hessian. Okay, cool. Okay, so then the question is, okay, can you expect something like this to happen for non-smooth optimization? And I know I didn't tell you what is an algorithm for non-smooth optimization yet, but I will. But for now, let's talk about continuous time. Okay, your basic algorithms in continuous time would be something akin to gradient flow. So here's a picture. So let's look at the following picture. So this is a C1 loss function, not C2, but C1, which is already going to be problematic, you see. So here's a C1 loss function. This point is critical. The gradient is 0. There's negative curvature. Okay, there's no Hessian, but there's still negative curvature in the sense that if you walk along this axis, it goes down quadratically. But now let's look at what happens to gradient flow. Like you would really hope that if you again initialize randomly, gradient flow will bypass such a point. But that's actually not true. There's a whole cone of initial conditions that are attracted to the origin. And by messing with this picture in high dimensions, I can make this probability be very large of ending up in this region. Okay, so there's something missing. Okay, there's like there's an issue. If you even go from C2 to C1, I even want to go beyond C1. So okay, there's some issue. It's not just curvature. Curvature is not enough. Okay. However, if you think a little bit about it, this function is not generic. If I tilt it a little bit, this issue will go away. And that will prove that in a little bit. Okay, so this pathological behavior actually disappears once you tilt the function. Okay, here's the opposite of that picture. This is where everything is great. Okay, so here's a function which again, this point is critical. Okay, and now I need a definition. What does critical mean? This function is non-smooth. There is no gradients. What I mean by critical, it means that the directional derivative is non-negative in every direction. That's going to be my definition of what it means for a point to be critical. I'm doing minimization. I want to be optimal up to first order. It means the directional derivative in any direction at the point in question better be positive. That's exactly what happens for this function, right? So directional derivative in these directions is strictly positive, and these ones it's 0. So this is a critical point. It is a crappy critical point because it's not locally minimizing. And again, you would hope that gradient flow would escape this point if you randomly initialize. And in this picture, this is true. Okay, so if you initialize the only initial conditions where gradient flow okay, subgradient flow makes you go to the origin is along the axis, so that has zero measure. If you start anywhere else, you flow away, go away. Okay, so it's this picture that I want to say is somehow generic around critical points of non-smooth functions. Okay, so now I need a definition. This is going to be my replacement for Moore's lemma. This is my canonical representation. This is my canonical property of a non-smooth function around critical points. Okay, so here's the definition. So I take a critical point. I'm going to say that the critical point lies on a C2 smooth active manifold M. So in the picture, M is the axis. Okay, if the following is true, the function f varies smoothly along M. So along M, the function is downward quadratic. So even though the function globally is not smooth, if you restrict it to the axis, it becomes a simple quadratic. So it's smooth, fantastic. And then what's very particular about this picture is the sharp behavior. You see this? So along this manifold, the function is smooth. And in orthogonal directions, it's sharp. Okay, and so that's part of the definition. So I'm going to say that as part of the definition, I'm going to ensure they require that f varies sharply in normal directions to M. So what that means is that if I look at any point x near x bar, and I look at its projection onto M, and I compare the function value, that's at least as large as some constant times the distance. Okay, so the function gap, is at least as large as the distance. So that models the sharp growth kind of deal. So that's my definition. And if okay, so this is good. Okay, good. So that's my definition. So again, I'm going to focus on this structure. Like this is the structure that I want to think about. The question of whether the structure is reasonable or not, whether it appears often, I will come back to. But that's the structure. Okay, good. So that's my somehow canonical representation of non-smoothness. And now I need to define what I mean by a strict saddle. Okay, remember for smooth functions, strict saddle means negative curvature. So I just emulate that. Our function is smooth along the manifold. So I'm going to just postulate that I have negative curvature along the manifold. Okay, so I'm going to say that X bar is an active strict saddle if it admits an active manifold. So we're in this picture. There's an active manifold. And F decreases quadratically along some direction that's tangent to the manifold. So formally, that just means that there's a curve in the manifold emanating from, sorry, this should be X bar, so that the second derivative of F restricted to the curve is negative. Okay, so you have negative curvature along the manifold. So again, in this picture, yes, you have negative curvature along the manifold. Okay, so this is a strict saddle, active strict saddle in my definition. Okay, so good. So this definition would not be particularly useful if it kind of didn't occur. Okay, so in fact, it occurs. So if I take, don't worry about this word for a second, but if I take some function f, then I do my usual thing. I make it generic by adding the tilde. And for almost every tilde, the following is true. Every critical point of this function is either an active strict saddle or a local minimizer. So in other words, for a generic semialgebraic function, don't worry about this word for a second, every critical point will lie on some active manifold for that function, and you will have negative curvature. So it's the exact analog of the basic SART kind of result we had in the beginning. Okay, so now going back to this word. Okay, this word is the thing that I need to make this theorem true. So semialgebraic just means that the graph of F can be written as a finite union of finitely many sets, each defined by finitely many polynomial inequalities. Okay, everything you see in practice is this. Okay, so if you're not comfortable with that word, pretend it is not there. Okay. The problem is that if you once you assume non-convexity and non-smoothness, Lipschitz functions, just like regular old Lipschitz functions, are extremely pathological. So you need to put some extra assumption even to make qualitative results. So the extra assumption that's over the past, I don't know, 5-10 years or something like this, has become very kind of mainstream in optimization is this, because it models more or less every problem you see in practice. Okay. Okay, good. Okay, so now I'm in the last part of the talk where okay, so the first part explains sort of what you do in the smooth setting, why this is not going to work in the non-smooth setting. We have, by the way, we have yet to see a matrix or an eigenvalue, but they will appear. The second part was to make this definition, which holds generically around every critical point. And now the third thing is I'm gonna make conclusions about algorithms. Okay, that's the third part. All right, so I'm gonna talk about two algorithms. One is for structured non-smooth optimization problems, and one for completely unstructured ones. So I'll start with the simple one, which is for structured problems. Okay, so a lot of optimization problems that are non-smooth arise in a very structured way, where the function you're trying to optimize is a sum of two functions. The first is smooth, like as smooth as you like. And it's the second one that's non-smooth, and like the L1 norm, for example, for sparsity, etc. Okay, so this is called a composite problem class. Okay, okay, so let's look at that. So f is going to be smooth with L Lipschitz gradient, and R is going to be some convex function, and I'm going to assume access to this function through the proximal operator. So this is very common when you do like application signal processing and so on and so forth. You need a way to access both R and F in algorithms. Because F is smooth, I'm going to assume that I can access its gradient, and R is not smooth. So what can I access? Well, I'll assume I can do a certain operation called the proximal operation. What that is I assume that R is sufficiently simple so that if I add to R a little bit of a quadratic, I can minimize that. Okay, so like if it's all the usual kind of regularizers, L1 norm, et cetera, this is all computable. Okay, and so this gives you the proximal gradient method. So this is the vanilla standard workhorse algorithms for problems of this type. It's just a generalization of gradient descent. So you walk in, so there should be x sub t, I apologize. So you walk from xt in the direction of the minus the gradient of f, the smooth bit, but you didn't do anything with r. So what you do is you do this proximal operation r. So if you imagine r is like an indicator function of constraint set, the prox is just the projection. So that would just mean that you walk in the direction of minus the gradient, then you do the projection back into the feasible region. Okay, so it's a very typical algorithm. Okay, good. So now I want to argue why does this algorithm, if I do the generic thing, add a little tilt, and initialize randomly, why does this algorithm avoid all critical points and just converges to local minimizers? So I just want to give a kind of intuition. Okay, so we need to come up with a fixed point equation, then connect something to, then argue that under whatever assumptions I'm making, that the crappy critical point is actually an unstable fixed point of the equation. So let's write down the fixed point equation. Well, it's staring at you, right? Xt plus 1 is prox, blah, blah, blah. This is some kind of, this is a map. You apply this map iteratively, but it's not smooth. Let's write it out a little bit more explicitly. Okay, so if you just remember what R was, R has to do with some minimization that has R in it and some quadratics. So if you just complete the square, you can equivalently really rewrite xt plus 1 in this compact way. Again, this is x sub t. Sorry about that. So it's really just minimizing some linear thing plus R plus some quadratic thing. And now a little magic. This is well known from like the 90s or something like this. If you have an active manifold, in the way I've defined it, if you run the proximal gradient method, eventually all the iterates it generates will actually lie on the manifold. Sometimes it's called the finite identification property. So eventually, because of this active structure, all the iterates of this process actually wind up on the manifold. And as a result, this argmin over y eventually becomes y argmin over y in M. Once this happens, by definition, R, well, whatever F, the whole function was smooth over M, and M is a smooth manifold. So this is just a really simple thing. It's just argmin of some smooth thing over a smooth manifold. You can try to do an implicit function theorem, differentiate, and argue about the eigenvalues of this operator. And so this is the one place where the eigenvalue appears. Okay, so around each active strict saddle point of f, we're going to define this iteration, right? This is the fixed point iteration. It's C1. It's C1. Okay, you need to argue. It's not automatic that this update is C1, even though you're doing argmin of a smooth thing over a smooth thing. Whenever you do an argmin, you might not end up with smooth things, but it works out. And in fact, the Jacobian of T has a real eigenvalue, which is kind of interesting because it's not symmetric, but it has a real eigenvalue that's greater than 1. This is magic. I don't understand how this happens, but it happens. Right, like like what's the assumption we're making? We're making an assumption about the function f itself having negative curvature along some manifold. Then we're looking at this particular map, which decouples everything. And it turns out that this negative curvature of the function itself, nothing to do with algorithms, tells us for some reason that the Jacobian of the update map, which is a property of the algorithm, has a real eigenvalue greater than 1. So they're coupled together. Okay, and so as a result, you're good to go. Randomly initialized proximal gradient method converges only to local minimizers on generic semialgebraic problems. Okay. I'm lying a little here because of your question, because this does not have a Lipschitz inverse, so you need to slightly damp it. You need to look at an average of T with an identity. But once you do this, this theorem is morally correct. Okay. Well, sorry, it's morally correct now. It would be correct if I made that small modification to T by adding a small multiple of identity. Okay, so that's my first algorithm, and then my final algorithm. How am I doing on time? Am I out of time? I think I am out of time, right? Okay. Okay. All right. Okay, so then I'll end here. I just have one last slide. Wait, 2 more slides. Okay. So now I'm gonna completely ignore structure, like totally unstructured. I have a Lipschitz function, and I wanna look at some particular algorithm for minimizing this function, and I wanna argue that again, if my function is generic, it will only converge to local minimizers. So what's my algorithm? My algorithm is really simple. It's gradient descent, but I'm not making up this algorithm. It's a standard algorithm. This is just great. This is just okay. If you know, it's just a stochastic subgradient method. But I don't want to introduce subgradients, so I'm going to hide all the details, hide all the complications. But let's do the following. I'm going to walk in the direction of minus the gradient. I'm going to sample a uniformly random vector zeta sub t and add that noise. Okay, so immediately you ask me, what does this symbol mean if my function is not differentiable? But because I'm adding noise and my function is Lipschitz, all the iterates ever encountered by this process almost surely are points of differentiability, because Lipschitz functions are differentiable everywhere. I'm adding a noise, isotropic noise. I'm only ever gonna encounter points where the gradient exists. I compute it. I walk in that direction. That's my process. Just completely standard algorithm. Okay. Okay. So now, when for smooth problems, you were allowed to take a constant step size, the 1 over L. For non-smooth problems, you need to make the step size decay to 0. And the reason is because imagine running gradient descent on the absolute value function. You'll just keep bouncing left and right. You need to damp the step size, make it go to 0. And the standard way to do that is to choose a step size sequence that's that's non-summable but square summable. So imagine like 1 over T, for example. Okay, so here's the theorem. For generic, again, semi-algebraic Lipschitz functions, if this method converges to a critical point, then it must be a local minimizer. Okay, this theorem sounds a little different from the previous theorem. And the reason is that there's a stipulation that has to converge to a critical point. So now here comes a caveat. This is kind of an open question. In general, this process, this gradient method, does not actually converge to critical points in our sense, in the sense where directional derivative is non-negative in every direction. Converges to a wider class of points called Clark critical. For most, so for those in those settings, this theorem does not apply. It doesn't say anything. Luckily, for many functions, there is no distinction between the two. But we couldn't quite know. We didn't really know how to deal with these other points that gradient method can converge to, besides the ones that are critical. Okay, so that's like an open question. How to deal with that? But somehow, again, morally, this is good. And I want to just give the last slide is just an outline of the proof because it's very cute. So there's a fundamental difference between how one approaches this kind of statement and how I did the gradient, the proximal gradient method. So you remember the main part of the proximal gradient argument was that eventually, because of this sharp growth, all the iterates lie in the manifold M. And so as a result, everything reduced to something smooth. My update map was smooth. Everything was smooth. Even though the original, even though the function is non-smooth, the update map is smooth locally around the critical point. For this algorithm does not have this property. The iterates here bounce around the active manifold. They don't hit the active manifold ever. So there is no reduction to anything smooth, right? You have this active manifold. You're taking these gradient steps. They vary wildly across the manifold, and you kind of bounce around. You never hit the manifold. There's no way to reduce, at least directly, to talking about something smooth. But there is. Okay, it turns out that this is actually the picture that is happening. So if you run this algorithm, this is sort of what the iterates are actually going to look like. So let's look at this. So this is this is the picture from before. So okay, so you run your algorithm. You go xk, next step, next step, next step, next step, next step, next step, next step. And you should notice something in this picture. The first thing you would notice is that the iterates xk approach the manifold much faster than they approach the critical point. In the sense that the distance from xk to the manifold appears to shrink much faster than the distance from xk to the limiting point. And the reason, and this is provable, the reason this happens is because of sharp growth. It turns out you can play with the sharp growth, which is the property, the key property of this active manifold construction. You can use that sharp growth to argue that actually the distance of the iterates to the manifold is on the order of alpha t, which is much faster than actually you can prove than the distance to the solution. Sorry, much smaller. So imagine alpha t is like, yeah, okay. Let me leave it at that. Okay, and then the second thing you argue, so in other words, you approach the manifold very, very quickly, super quickly. And then the second key thing you can argue is the following. If you actually look not at the iterates themselves, but at their projections, so like these red points that are in the manifold, right? Those projections satisfy a funny recursion. They look like a gradient descent update, but not gradient. It's actually the Riemannian gradient of f plus an error term. And the error term is only on the order alpha squared. Whenever you see an error term on the order alpha squared, you're very happy because alpha is small, so alpha squared is way smaller. And so as a result, you can leverage the smoothness of these shadow sequences in order to argue about escaping. And the key part in this argument is the noise term. So here I kind of played a little bit fast and loose and said, oh, okay, I introduced this noise term just to make sure gradients exist. That's a lie. The noise term is key in order to make sure you escape from saddle points. It's this excitation phenomena, and it was kind of discovered in the 90s by Pimentel, that you can escape kind of unstable fixed points by introducing isotropic noise. That's the game that's played. Okay, good. Okay, one other thing I lied about. These two things require slightly more than just the definition of an active manifold. They require another property which is technical, so I didn't include it here, but it comes from something called, this is for the experts, the Coer-Verdier condition stratification theory. Okay. So you need to somehow compare, you need to be able to compare the gradients outside the manifold to the Riemannian gradient. You need some kind of Lipschitz condition. And this Lipschitz condition is not a thematic, but it's generic as well. Okay, and so that's the argument. And like I said, in terms of stochastic processes, there's quite a lot of work in adapting some techniques from Pimentel to make this all work out with the error term. Okay, so there are some references. Mainly it's the top two, and then there are a couple of other ones that are related. Okay, thank you.